I'm asking the session host, technical host.
Yes, yes.
Yeah.
Yeah, so you can just share your screen. I should be able to share your screen.
Sure, 1 second.
So the first
Okay.
paper, as you all know from the program, is quite exciting. What would happen if all countries in Europe adopted the Swedish carbon tax, the level of the Swedish carbon tax? So we're looking forward to your presentation. And the presentation is by Eoin Ó Broin, as you can see. So you have half an hour from now on, please.
Great, thanks, Katie. I'm affiliated with CIRED in Paris and also with Envicon, Environmental Economic Consultancy in Dublin. This work is a collaboration with the University of Gothenburg and IVL, the Swedish Research Institute. It's funded by Formas, and we've been funded for a couple of years to do studies on the European residential sector, some policy analysis, and we use econometrics and simulation. So my study today is what would have happened if these large EU countries, who were all in the EU when we started this study, had adopted the Swedish level of carbon tax for their resident, well, what would have happened in the residential sector. What we find is that there would have, for these 5 large countries, there would have been a 15% reduction in their in the CO2 emissions from the residential sector. So I'm showing the results now, but I'll go through how we got to here from now on. First, the Swedish carbon tax is famous because it's so high and it's been consistent. It started in 1991. At the start, there was 2 levels. The industry had a lower level. It was 24 euros per ton for the residential sector, typically, which would affect heating. It went up to 87 euros per ton by 2004, and now it's 114 euros per ton. And there's no longer a derogation for industry. Looking at global comparisons, you can see there, this is in dollars now, Sweden has the highest with $137 per ton. And then you have Switzerland and Liechtenstein at 101, and then down to Finland. And Ireland, where I live, is $39 per ton. It's applied to fossil fuels. So for the 3 fossil fuels, coal, oil, and gas, there are differential rates because of the higher carbon intensity of coal versus oil versus natural gas. So that's the actual cost per megawatt hour for the 3 fossil fuels. This diagram shows the demand for fossil fuels in the residential sector in Sweden since 1970. So gas and coal almost don't exist. There's some natural gas used in restaurants for cooking, but there's no gas network, so to speak. Coal may have been used a long time ago, but certainly not in any recent times. In 1970, oil made up over 75% of energy use in the residential sector, and this has fallen to almost nothing today. Energy use in the residential sector across the EU typically makes up 1/4 of the total energy use in the economy, and of this, 2/3 is used for heating. So that's what the diagram on the right divides up the residential sector energy use into the end uses. This diagram shows the energy balances in 4 of the 5 big countries we're studying. The blue is natural gas, the yellow is oil, and the green is other, which can be biomass. or district heating or new renewables. You can see there's a huge use of natural gas in the UK, while in Germany, there's still a significant usage of oil. There's almost, coal is almost gone in both the UK and Germany. What we try to do then is to take the prices which exist for fossil fuels in the large EU countries and increase them by the level of the Swedish carbon tax, and then see what would the resultant fall in demand be, and what would that result in greenhouse gas emissions. To do that, we need to know the price elasticity of demand for across our set of countries. So we have a panel from 1990 to 2015. The variables are demand, a weighted average price for 5 energy carriers, income, a proxy for the weather, heating degree days, and then the number of dwellings, which also relates to population growth and changing household size, so as families get smaller. If you look at the weather data there, you can see that the minimum 1,485, that would have been a warm year in Spain, and the max there 5,874, that would have been a cold year in Sweden. We set up a dynamic panel with our variables, and we do a couple of different models to account for the well-known biases that can occur on the calculation of the coefficients due to the correlation between the lagged dependent variable and the fixed part of the error term in dynamic panel data. So first, this is the results of the panel econometrics to find the price elasticity. The first row there is the lag of energy demand. The second row is the price that WOT is weighted average price, the price elasticity. The next row is the income elasticity. Then the elasticity of the climate with the heating degree days. Then the dwellings. And then we introduced a trend as well. And the models, the coefficients calculated in the models are almost the same, which suggests there's no bias in our data set. The price elasticity is minus 0.22. That's the short-term price elasticity. So when we combine that with the lag, we get minus 0.39 as our long-term price elasticity for the group of countries for the residential sector. These diagrams show the prices for the fossil fuels in the different countries. On the left, you can see the prices are all clustered there. Between in 2018, almost 80 euros per megawatt hour in Spain. Then the lowest one is 50 euros per megawatt hour in the UK. The red is the level of the Swedish carbon tax applied to natural gas, so that will be added onto those prices. The navy is the Swedish price for natural gas with its carbon tax included, so you can see how much higher that is than the rest. On the right hand side, for oil prices, it stands out that Italy had really high oil prices as compared to the other countries, and the Swedish oil price, including carbon tax, has caught up in recent years with the Italian price. And again, the red line there is the carbon tax applied to oil, which would be added to those of the prices from the other countries. On the right there is our simulation equation to see what is the change in demand when the prices go up. So we've the new price divided by the old price weighted by the price elasticity, that's minus 0.39, that's the beta, to weigh the existing energy use to get the new energy use. And if we look at the diagram, the heavy lines are the measured use. That's what actually happened. And then the dashed line shows how much the use would have fallen if the prices had been higher. So you can see that there's a large fall, would have been a large fall in demand in the UK, and not as large for Germany. If we combine looking at all of the fossil fuels together for the three countries, you can see that there's a large fall for Germany because there's so much oil used there in addition to the natural gas, and also a large fall at the start for the UK. So again, just to emphasize, this is residential sector. The heavy lines are what are measured demand for the fossil fuels in the residential sector, oil plus coal plus gas. And the dashed lines show how demand would have reduced if the prices had been higher. When we use the carbon intensities of the three fuels, we can calculate the resultant emissions. So everything in orange, including the dashed line, are the emissions that did occur from the residential sector, and the dashed area shows the reduction that would have happened if the demand hadn't been so high. So that was our initial approach: increase the prices, use that in combination with the price elasticity to see what's the fall in demand. But a criticism we got was that, what about fuel switching? Because it's certainly occurring when we look at the Swedish case, where the oil use has almost disappeared, and it's not just from efficiencies. Like the entire stock is not passive houses. So something has happened there, and it wasn't clear that we're capturing that. So we came across a paper by Julius Andersson, where it's a study of the Swedish carbon taxes applied to the transport sector in Sweden, in particular gasoline or petrol use. And on the left, this is a diagram from Andersson. The heavy line at the top, the dark line, that is the gasoline price. Below in gray, you've got the energy tax, and then below that again, you've the carbon tax and VAT. And if you combine the three lower ones with the wholesale price, you get the gasoline price. And Andersson's time series was from 1960 on, and what he decided to do was to see if there's a separate elasticity for the price as opposed to the carbon tax itself. So these are results from Andersson. The first line is the elasticity of gasoline in the transport sector in Sweden. The next line is the carbon tax elasticity. So Andersson separates out the price without carbon tax from the carbon tax, even though to the end user it's all in there together. And what we thought is that the carbon tax elasticity can also include fuel switching, because perhaps it sends it's the signal that economists talk about, that it lets society know that prices will not be going down, and it's, you know, a change has to should happen. In Andersson's model, he includes a dummy variable for the carbon tax because it only comes in 91, although his data set starts in 1960. He includes a time trend, GDP per capita as a proxy for income, an urban variable, urbanization, because in cities, obviously, you've public transport, which can change things, and the unemployment rate. And if we look at his fourth model there, where I've underlined in blue, you can see that the elasticity of the carbon tax is 3 times higher than the price elasticity. He instruments for these two variables as well and doesn't find any difference. So that's the key thing. He finds that the carbon tax elasticity is 3 times higher than the price elasticity. So maybe this is because of the way it sends the signal to society. So if we're taking that as including fuel switching, one option we have is that we can simply multiply our price elasticity by 3, as Anderson has found. But perhaps even better if we calculate our own carbon tax elasticity for the residential sector. So when we just multiply the elasticity by 3, you can see there's a larger reduction in there would have been a larger reduction in greenhouse gas and CO2 emissions from the residential sector for the time period. I forgot to say, we start in 97 because that's when the Kyoto Protocol started. It would be unrealistic to think that countries would have adopted the Swedish level before that. So, but how to establish our own carbon tax elasticity for the residential sector? Well, we can't study oil or gas or coal because they don't they're hardly used. So we have to do a model of oil demand for the residential sector. we do that, and these are the models I'm showing you here. In the first model, we copy exactly the variables that Anderson has used. So the first one is the price, the oil price without the CO2 tax. The second variable is the CO2 tax applied to for oil. In both cases, we add VAT. Then we've a dummy variable for when the carbon tax kicks in. We include the trend, income per capita, and then the same urbanization and unemployment level variables. And in this model, however, we don't get a significant price elasticity, and also the dummy variable is positive, which that's not intuitive, as you would assume that when the carbon taxes arrived, energy demands started to fall. And examining that model, we found that the trend was causing collinearity. So we removed the trend, and then in the next model, you can now see that the price of oil is significant, and it's minus 0.01, whereas the carbon tax elasticity is minus 0.03. So we're in the same territory as Anderson, finding that the carbon tax, it looks like it's 3 times bigger than the price elasticity. Well, we've been working with energy use in the residential sector for a number of years, and we almost always have the HDD variable, which is the proxy for the climate. As in colder weather, energy use increases, and something connected to the number of dwellings or floor area or household size. So we introduced those 2 variables into the model, but didn't find either to be significant. So when we remove the non-significant variables, we get this fourth model here, which has the same results for price and carbon tax elasticity, and the dummy now has the polarity that you would expect. The income has a negative polarity, which is counterintuitive, but it's very small, and some people argue that as income is rising, people are investing in more in energy efficiency. The next question we wanted to answer is if these variables are co-integrated to make sure it's not a spurious regression. So we use the bounds test. This is implemented in OR. An AIC test suggests that the best model is this 1110, where we've one lag of the dependent variable, one lag of the price variable, and one lag of the carbon tax variable. The F value we calculate is 9.3, which is quite above the upper bound of 4.45, which tells us that the model is there's co-integration between the variables. In order to get this, though, we had to drop the urban variable. Using the bounds ARDL approach, we get slightly different estimations for the price and carbon tax elasticity. So minus 0.026 for the price and minus 0.045 for the CO2 tax. So in the ratio for the ARDL of those two results is 1.7. So the carbon tax elasticity is 1.7 times greater than the price elasticity. And in the best ordinary model, it's 2.3. So we assume that the carbon tax elasticity is twice as big as the price elasticity. On the left, you see the results I showed at the start for an elasticity of minus 0.39. And on the right, you see when we double the price elasticity to incorporate that when it's the carbon tax which causes prices to rise, that there's a higher elasticity. And when this occurs, if this had occurred for the residential sector of the 5 big countries we've studied, there would have been a 26% reduction in CO2 emissions. When we were looking at how to use this work, we plotted for the 5 countries and Sweden for illustrative purposes the non-ETS emissions targets for each country. So if let's take France here, so this was their 2020. This is their 2020 target, and this is their 2030 target from the base here in 2005. So the yellow is the measured emissions, and the blue is what the emissions would have been if the carbon tax had been at the Swedish level. So you can see France was approximately on track to meet its 2020 target, but if the carbon tax had been higher, it would certainly have been on track. That's the work. The conclusions are that it's with the long run price elasticity of minus 0.39, there would have been a 15% reduction in CO2 emissions from the residential sector of 5 large EU countries if the Swedish level of the carbon tax had been adopted. And if we attempt to incorporate fuel switching by using the elasticity of the carbon tax, the reduction could have been higher at 26%. That's my presentation. So my question to you is, are you convinced?
Thank you very much, Eoin. That's great. Let's have questions from the floor. We have 5 minutes for questions. Otherwise, I'll start. You answered my first question, because basically in the beginning, yeah, I'll take Paolo. In the beginning, you talk about gross prices, right? Inclusive of everything, carbon tax, VAT. So it's not really an effect of the carbon tax that you find. It could be an effect of the VAT, the energy tax in Sweden that's very high. That's not a carbon tax, that's just a general energy tax. So I appreciated that in the second part then you actually tried to decompose at least the VAT and the carbon tax.
Yeah, Anderson has a nice diagram.
Yes, I know the paper.
Okay, good. The thing which I learned from it is if we look at, let's see, here you can see there's a large increase in the carbon tax from 2001 to 2005. Let's even go to here, like this slope here. And it seems astounding that any government would be able to manage such large increases. But what I got from Anderson is that they simultaneously reduced the level of the energy taxes. So the consumer didn't really see that large increase.
And then we have Paolo has a question, please.
Yeah, thank you. Yes, I have a question actually on if there is any insight also related to how the what is the impact on the overall economy of such a reduction of the carbon budget, because I assume that this will pressure the system of these countries to move from these fossil fuels towards electricity and towards possibly hydrogen. But this will probably also push the price of these commodities up, and also will have an impact, for example, on the profitability of energy intensive industries, for example. And yeah, so my point is,
I don't know. We haven't done any equilibrium modeling to look at the impact on the economy. It's just, we just focus on the residential sector. I mean, anecdotally, well, what has happened in home heating in Sweden is that up until the 1970s, the countryside houses used oil boilers to heat, and in the cities, district heating had started, but the district heating itself was arrived from oil and coal boilers. What has happened is in the countryside, those oil boilers are nearly gone. They're replaced with biomass, or what do you call them? Water to air heat pumps, and sorry, grounds to air heat pumps. And in the city, the district heating is the heat comes from waste heat or biomass. So, I mean, okay, it's not an economic sector like industry, but that's the transition that has happened. Yeah, as far like Sweden would be big with mining and paper pulp. So I just know from colleagues that these in this particular, maybe the paper uses biomass for its heat needs as opposed to oil and coal. So has it affected the overall economy? I doubt it.
Okay, I see. Yeah.
If I can add, there are economic studies evaluating that, showing a very very small economic impact on the general economy. And that comes, Eoin, you showed the graph before about the exemption of industry. So basically, I mean, now there isn't any, but in the beginning there was a large exemption for industry that then gradually was phased out. And this may explain that there was a smaller impact on industry, and the major burden was borne by households. So just to add that, I mean, you showed that yourself in your presentation. And then also the general reform of the energy taxation, as you mentioned, that the carbon tax component was increased at the same time as the energy tax component was decreased. So the overall tax burden remained about constant. Yeah. So one other question maybe from the floor before we pass on to Paolo, because I think we have some more time. We have only 3 papers and I haven't seen the third speaker yet. Otherwise, I have one more question. When you do your last, you know, the last table you showed on your regressions of the oil demand, that said total oil demand, but shouldn't you just look at the residential oil? I mean, the demand for heating oil.
This one, it says total. It's total oil in the residential sector.
Okay, great. So then, and then I agree with you that I don't really see why you would put in urbanization. That's important for transport fuel demand, I guess, but for heating, I don't really see it. And I would rather see that the heating degree days, I was surprised also they're not significant because it's extremely important, right? Particularly for Sweden, if you compare southern Sweden and northern Sweden and the heating demand, I was very surprised by that result.
Every other model we've done, it has been in there. There's something, I think there's something special about this, that the oil use is falling all the time. It's almost like there's a trend there, regardless of the other, you know, everything has an impact. Let's see, does it rise at all? So there, like in 1975, you know, you would typically say maybe that was a cold year, 1975, and does it really? There's not too many bump, maybe 95, a slight bump, but yet typically you have a little, you can see the spikes in the cold years. And that's, the HDD picks that up, but not in this case.
Okay, thank you very much.
Maybe we need to do a few more tests around that.
Thank you very much for your very clear presentation. And now we should pass on the word to Paolo, who's presenting a paper on the European energy transition. So the floor is yours for half an hour.
I'll share the screen.
Can you share your screen?
Let me just move this away. I believe you can see that, right?
Yes, perfect. Thank you.
Yeah.
Good. So, okay. So good morning, everyone. I'm Paolo Pisciella. I'm a researcher at the Department of Industrial Economics and Technology Management at NTNU. I'm presenting an economic evaluation of the effects of decarbonization in different European countries, considering on one side the push provided by the carbon prices, and on the other side the pull, let's say, provided by the technology development, as well as the consumption development. The work is done under the Open Entrance project, the ongoing, and it's work done together with my colleagues Thorsten Burandt at TU Berlin and Pedro Crespo del Granado at NTNU. So this is the outline of the presentation. I will introduce the motivation, touch briefly on the models employed and their linkage, and then introduce the scenarios that we have developed for this exercise. So as we know, the plan is to decarbonize Europe by 2050. So some countries have in the past shown signs of skepticism over the climate goals and mentioned that they could call off the agreement. Our question then has been, what are the effects of a transition towards a cleaner economy for Europe? And what happens if there is a defection by a group of countries? And in this study, we will consider the impact on energy commodities demand, well, general price, then and particularly value-added GDP, depending on the level of decarbonization on the scenarios that we analyze. So some of the questions we might want to ask are considering an increase in productivity for renewable sources. If this increase is good to offset the lack of fossil fuels. So is it enough? If the pull by the technology development is strong enough to cope with the push by the policy. Also, we want to see if all the countries have the same effect from a decarbonization policies and policy, and why. So is there any country that is basically better off if they call off the agreement, and what are the possible countermeasures if they call off the agreement? So we have analyzed the problem by soft linking two models. One is called REMES-EU and the other one is called Genesis Mod. So REMES-EU is a multi-country CG model considering several types of fuels and the effect of CO2 budget on the economic system. It considers basically 28 countries, which is the EU 27 minus Croatia, so prior to 2007, but includes Switzerland and Norway. On the other hand, the bottom-up model is Genesis Mod, which is an energy system model capable of computing the future mix of energy technology used by different sectors based on a global least cost approach, and uses a detailed technology representation. So a little bit of a detail on the linking. So Genesis Mod provides a technology-rich dynamics. So basically, it gives the dynamics of the technology changes in terms of energy inputs requested by the different sectors and the final consumption. So this dynamic of the technology changes is considered as an input to in the economic model in REMES, which computes an equilibrium between demand and supply as the technology and the policy changes, and provides so computes basically a new economic equilibrium, and provides Genesis Mod with the level of sectoral activity for different sectors, the CO2 prices, and the electricity demand by sector. So both models work on a 5 years time granularity. So the analysis that I'm going to show can be viewed basically as an economic evaluation of the results provided by Genesis Mod for the scenarios that I will be discussing afterwards. So I can go on. And so a little bit more about the linking here. So one, say, sort of problematic part, or one of the hardest parts, or anyway, even better, it's something that you could consider simple to do. I did consider simple to do, but it was not. And it's the harmonizing process between the inputs of the different sectors. So it was actually quite challenging. Basically, REMES, the CG model, uses monetary units, while Genesis Mod database uses physical units. Sometimes there are commodities that are featured in the social accounting metrics, which is the data that is used by the economic model here, the REMES. And these commodities are present in the data for the economic model, but they are not in the energy system model for some sectors. And this also happens because of the aggregation of sectors. So maybe can be a little bit different. So there might be a sector very aggregated in REMES that uses coal, because basically it's an aggregation of different sectors, so that's why. But the same sector with the same name, or the corresponding sector, doesn't have coal at all in Genesis Mod, because maybe the quantity is very small, and it was just REMES as the purchases, that there's been during a year from a particular sector. So it could be that that for some reason there was some coal purchased, but it was not used in the production itself directly, so it's not featured in Genesis Mod. So it can happen that REMES has it in the data, but Genesis Mod doesn't. On the other hand, we can have the opposite. Actually, it's more not more often, but it can happen the opposite as well. So we had to work a little bit to harmonize the information on the technology. This is, for example, this is an example of how I don't remember. Yeah, the households in this case, the energy consumption in the households changes over time in Genesis Mod and in REMES. So we have different colors, but this is, for example, the one in the upper part here is electricity in Genesis Mod. This is quantity-wise, and this is electricity in REMES that is monetary wide, let's put it like this. And they follow the same, say, type of development, but they have different percentages, because here the database in Genesis Mod was done with physical units, and this was made with monetary units. So it's possible to harmonize. For example, even more, we have a difference here that I believe it's it's biofuels here and here. So it's way more, we can see here. And this depends on the fact that what we're doing is that we are using a multiplicative change in REMES on the percentages of usage of a particular fuel. starting from the percentage change in Genesis mod. Sorry, yeah, here. And yeah, so it can happen that the percentage goes out high faster anyway. So yeah, we had to use some tricks to make it work. So about the scenarios that we have defined a couple of axes. One axis is about the level of decarbonization. We have a sort of a business as usual side and a decarbonization side for these European countries, for this EU27. And on the other axis, we have the level of cooperation between the countries. So depending on the level of decarbonization and the level of cooperation, we have defined these 4 scenarios here. In all the scenarios, we have an expansion of the renewable sector, power sector. In the business as usual scenarios, we have a lower policy push, which means that is given by carbon budget. So here we will have a higher carbon budget, which will lead to a smaller carbon price. On the other side, we have a lower carbon budget, much lower, which leads to a higher carbon price and therefore to a stronger decarbonization push. Now, on the other side, what we have is that the carbon budget, on the non-cooperation case, we have considered some European countries, in particular the Visegrad 4, just as a test, basically. We assume that the Visegrad 4 do not cooperate if there is no cooperation. So these countries do not use any carbon budget, or anyway, they use it, but it's much higher. So basically it will imply a much lower carbon price. So in these 2 cases here, but what I will do here, I will focus on the business as usual cooperation case and on the decarbonization cooperation case, and make an analysis of these 2 cases, and then I will comment on what happens if we have no cooperation in case of decarbonization. So what happens in particular, what is the impact on the economic growth of different countries in particular. So these are the main assumptions that I've used, that we have used in the CGE model. In particular, we have that CO2 allowances need to be purchased by every sector consuming fossil fuels. So we have not made any difference between the sectors that are under and sectors that are not under a regime of CO2 allowances. So all the sectors using fossil fuels need to buy CO2 allowances. The CO2 budget is defined per country. Then the technical change is an input from the energy system model, as I also have stated before. The energy intensity improves over time, while we have not modeled carbon intensity. It's just energy intensity that it's leading to a lower purchase of energy commodities besides the CO2 price. Also, we have exports of hydrogen. We have a new sector compared to today, a large-scale hydrogen sector that is exported, and we assume that the initial exports, sort of for making a calibration of the model, the initial exporting structure is the same as the one for natural gas. Finally, the renewable productivity increased by 6% every 5 years in the business as usual scenario. Also here I make a difference between the business as usual and the decarbonization. So besides the assumption that I have already stated, the main drivers for the macroeconomic dynamics are the reduction of CO2 budget compared to 1990. So in the business as usual, we have assumed a reduction by 60%. In the decarbonization case, we have assumed a reduction by 90%. Then again, as I said before, we have the inclusion of a large scale hydrogen sector. There is a shift toward the consumption of electricity, biofuels, and hydrogen. This happens mostly because of the CO2 price. Oops. Then we have energy efficiency improvement, which are by different intensities in different countries. We have renewable sector productivity growth, as I said before, 6% every 5 years in the business as usual, and we assume that there is an even further technology push in the renewable sector productivity in case of decarbonization, and it's pushed to 10% every 5 years. Finally, we assume that we reduce the extraction of oil, gas, and coal by 50%. Well, here not in the business as usual. We assume that it does not increase the extraction. It stays the same as the base year, which is 2010. And here we assume that it decreases by 50% every 5 years in the decarbonization case. So I'll go on the macroeconomic effects a little bit. Explanation of macroeconomic effects. So now the point of first impact on the shocks is the demand of energy, basically demand of different energy commodities. Therefore, we start from the development of demand under the two scenarios with collaboration, though. So we have, this case, we have business as usual collaboration, of course, here. And here we have decarbonization case, still collaborative pattern among the different among the different countries. So we can observe that there is an overall, so even here, in the business as usual, we can observe that there is an overall decrease of energy consumption, which depends on two factors. One is the increasing energy efficiency. So here we have both actually, in both cases, we have energy efficiency and carbon price, but here is much smaller, the carbon price. And we can also see that there is not much change into the fuel switching. Yes, there is more, a little bit more electricity, a little bit less, natural gas and crude oil, and a little bit of hydrogen that is coming in, but it's not that big. This switch. But when we go on the decarbonization case, due to the higher carbon prices, we can see how the structure of the energy consumption changes. In particular, there is a large increase of usage of electricity, quite larger increase compared to the business as usual of the hydrogen usage, and also increasing in biofuels. Besides the complete sort of phase out of the usage of crude oil, and a decrease in usage of natural gas, quite decrease if we compare to the business as usual case. It's quite a big decrease also. So yeah, basically in the decarbonization scenario, electricity, hydrogen, and biofuel take over the decrease in fossil fuels. Even though the decrease, the total decrease in usage of energy is it's more, but not that much more. Yeah, well, something anyway. So what happens to emissions in the two cases? So the emissions decrease already under the business as usual, but they only reach 60% decrease. As we can see, it is around 60% decrease compared to 2005. Sorry, not 2010 here. And while under the decarbonization case, the decrease is by 90%. The first thing that we can notice here is that the industry, which is this dark red part here, does not decrease much the emissions. And what we have noticed is that this happens due to the technology mix development passed by the bottom-up model. So the industry basically does not completely get rid of natural gas, heavy distillate, and some other fuels. So so the economic model is computing a new solution, provided the evolution of the energy mix that is purchased by, or that is required by, the different sectors. So if these sectors are not completely transitioning towards a clean source, and they keep using gas, for example, especially in this case as in the industry sector, it will happen that they will keep being in the economy, and this will have consequences in both in the carbon price and in the economic growth of these countries. So yeah, so this means that in particular that industry will have to pay quite a penalty in terms of CO2 allowances. So this is also to give an idea of how the CO2 price, how the expenditure for CO2 allowances changes over time depending on the two scenarios. Business as usual, it reaches around not even 200. Decarbonization, it's 6 times higher. So I mean, this is not really, you know, it's not a forecast. We're using a CGE model. It's, we don't make forecasts with a CGE model, but just to give an idea how the order of difference between the two cases. So when we need to decarbonize more, and if we don't completely kind of transition the energy structure of a particular of the production sectors in particular, will have a much higher price for CO2. Of course, if there is a faster sort of technology development that leads the different sectors to get rid of fossil fuels, this price is not that high. It will be lower. So this is what happens in the two cases. These are both cases with cooperation, though. So sorry. Also have reported what we had as prices without the implication of this transition in terms of energy prices. So we have that in general, the business here. So we're looking at the business as usual. We have that prices for energy commodities tend to decrease in proportion to the consumer price index. And this is basically, it's mostly due to the energy efficiency in this case, but also a little bit related to the fact that we have a CO2 price. It's not that high, but we have it. So so this means that if a CO2 price decreases the demand of a particular fossil fuel, and this demand will, the decrease of demand of fossil fuel given the supply that doesn't change, will decrease their prices. We have a couple of exceptions. One is electricity, and the other one is heavy distillate in this case. For what concerns electricity, we have the electricity prices. So it's the gray one here. It's slightly higher, as we can see, not that much higher, but slightly higher. The electricity price increases due to the increased usage in industry, and yeah, the growth in this case, the growth in the diffusion of renewable sources is slower. We have modeled a quite a slower diffusion of, sorry, I can't see my pointer. There you go. We have modeled a quite slower diffusion of energy of renewable sources. So the price in this case, it's higher because we need more of it, and we do not necessarily have a much larger increase in capacity. So this is what happens in the business as usual. We will see that in the decarbonization case, we have modeled a much higher increase in capacity, and therefore this will lead to a decrease, even if we have much more demand. The other case, the other commodity is heavy distillate. Is what happens is that at least here we are examining Germany, the price increases, so it's the green one here. It increased because of its production does not increase any longer, actually decrease a little bit due to the fact that we are slow, that we are not increasing the amount of crude oil that extractions. So we are definitely not increasing the production of heavy distillate, but its usage actually is not changing either. So since we are sort of reducing the usage of other energy commodities, fossil energy commodities, in the structure provided by the bottom-up model is maintaining, in Germany at least, the usage of heavy distillate, in particular in industry, as we have seen before. We have seen from here, we see that industry is not decreasing the amount of fossil fuel, and this happens in particular, like in Germany here, where we have still heavy distillate in the technology mix. This leads to an increase in price, and yeah, and while the others are decreasing, the other price for other commodities besides electricity. In case of decarbonization, actually, there is a larger increase of heavy distillate price, still for the same reason. It's still used in industry. We have shown here both this was the business as usual, but we have shown also the decarbonization case, and we don't have such a large decrease of emissions in industry. This is also due to the fact that we are still having some particular fossil fuels in the mix. This is the proposal that we have had from the bottom-up model, from the Genesis mod. So since we still have heavy distillate in the mix as a required fuel, and since we are decarbonizing with a quite heavy carbon price at this point, there is going to be, first of all, there is going to be a much stronger decrease of prices for other commodities, because we are not buying any longer these commodities. We're buying much less. This, we keep buying it, and yeah, we keep buying it even more, and its price is and its price is even going higher, because, well, because we are reducing much more the usage of these other ones. So we are buying it, we are spending more for this particular commodity, and we are paying a much higher carbon price. The point is, we need to decarbonize fast if we want to push more from the say, on the policy side. If we want to have a very small carbon budget over time, we need to, the faster we are in technology transition, the better. So that's pretty much the idea here. So here I show, so I go directly on the impact on GDP as a, basically it's as a percentage change compared to the business as usual. So this is so here I'm taking 2050, and I'm checking what happens in case of, first of all, decarbonization. So we had first business as usual is the reference, so it's 0, it doesn't change. Then we have a change in case of decarbonization with cooperation. It's the blue one. Then we have a second case, which is decarbonization with non-cooperation. So basically here we have that some countries, the Visegrad 4, are calling off the agreements. They are not cooperating any longer. But what happens is that they get a tariff on imports of any product, not only energy ones, but any product. The idea is that they are producing at with a sort of with a fossil structure. This leads to cheaper products for them, and they might want to export them, and therefore a possible response is to put tariffs in the imports from the Visegrad 4 products. And on the other hand, we see what happens if we don't have collaboration, but at the same time there is no tariffs. So in the first case, so first of all, we notice that when we have a decarbonization, well, in this case, we have a decrease percentage-wise of GDP. And this decrease is higher in the Visegrad count, is quite high, actually, not higher, but it's like Bulgaria, Czech Republic, Hungary, and Poland, they have quite a high reduction. This is, and this is actually the biggest reason is the speed in change of technology input. So how much they are developing their energy structure in terms to transition towards a cleaner structure. So if you're slow and you're having carbon tax, then you lose quite a lot. The prices will increase in general, and the economic activity will decrease. So in the second case, we show that if we have if these countries call off the agreement, they have an improvement. So Austria is not in the Visegrad 4, so it doesn't have an improvement. But for example, if we go to Czech Republic, there is an improvement. So there is minor losses in this case. Hungary has quite a good improvement, minor losses. Poland has quite a good improvement as well. So what happens is that in this case, though, they have, but in this case they have taxes anyway. So if we go to Hungary here, yeah. So if we have taxes, still there's an improvement, but in the sense that they don't lose much. Yeah, but but it's not. So it's not going to be as bad as when there is when they are following the Visegrad. Sorry, when they're following the carbon climate goals. In the other case, so what happens here is that so it's the second one is with tariffs. The third one should be is the one with, okay, the third one is the case without tariffs though. So in this case, we're not making them pay anything, and they can start exporting towards other countries, and this makes them actually quite not to say efficient, but competitive. They can by allowing them to not pay taxes and to use a dirty sort of production structure, they basically keep they have a growth because they have a competitive advantage compared to the other countries. The interesting thing is that by putting a tariff on the imports of all these countries of these Visegrad 4 countries, actually the other countries are worse off. As we can see, for example, from Germany, when these tariffs are eliminated, the tariffs on imports from Visegrad countries, Germany is, but also other countries are having lower losses in terms of value added, in terms of GDP. And this actually, well, we're looking further on this, but it seems that it boils down on the fact that these countries can export, can keep exporting fuels towards the Visegrad 4 countries that can take these fuels, use them at a cheaper price for production, and then they can export. You know, they can or they can not necessarily export products, but also produce internally products that are cheaper, and therefore their economy can grow compared to the business as usual. So in this case, what we're having is that without basically the tariffs, the clean countries can sell fossil fuels to Visegrad and gain on these sales, but while the Visegrad countries will produce at lower costs and possibly also export at lower costs.
So you have 5 minutes.
Yeah, but I guess it's the last slide or the second last. So yeah, we just have comparison between the difference in terms of emissions. We can see that in the case of non-cooperation, of course, the emissions increase because of these countries not participating. Also, what we have modeled is that in the non-cooperation case, there is a the other countries, the ones that are participating in the decarbonization, they are decreasing the carbon budget even more to try to reach the 90%. But yeah, basically we took something like instead of 90%, we made it 95, but still it's not enough, it seems like. So, and yeah, so we will still have a larger, you know, a smaller, let's say, effect on the carbon budget. That is not, it's decreasing, but not as much. So yeah, I just jumped to the conclusions. Actually, next slide was. So in a way, we can say that the decarbonization policy needs to be accompanied or anyway done by the side of a technological transformation of the production sectors. This is what we have detected out of the simulations. So the faster the transition towards a cleaner structure, the better, especially if we have a strong policy push using high carbon prices. So not all of the countries have the same impact from decarbonization policies. So the more resistant are the countries whose technology change is higher. So basically, if we are resistant to technology change, then the impact of CO2 price is higher on the growth. Then the increase in renewable sources might help fostering economic growth as long as the technology moves the same way, accepting electricity as main source, as main energy source. So everything boils down on the relative speed of change of what's called technology structure, technology development in terms of fuels that we are consuming, and the push by CO2. And then at the end, putting tariffs on imports from countries that are calling off to countries that are calling off the agreements might actually lead to a decrease in GDP of every country, also the ones decarbonizing, because basically they cannot. Basically we are not. What we are doing is that we were not sort of asking the countries not to produce any more fossil fuels. We were asking not to use them anymore. But if they can produce or extract them, and they can, whoever has the access, of course, to these resources, and sell it to someone, in this case to the Visegrad 4, they will be better off financially. And I mean, of course. And of course, the Visegrad 4, if they can, or whoever. Here we took the Visegrad 4 as because we read a newspaper article where they were menacing to call off the agreements. But any country, this applies to any country that might call off the agreement, if they have the possibility of using a dirty structure and then also export. Of course, they will be better off both internally and because of the exports. So bottom line, it has to be the technical change needs to be at least as fast as the push provided by the CO2 prices. And that concludes the presentation.
Thank you very much, Paolo. So we have 5 minutes for questions. And I can start. Maybe I had a modeling question. So you're not really modeling a carbon tax, you're modeling carbon allowances, right? And you're making this
Correct.
huge extension that it's all sectors that are covered. It's not like in the current EU ETS, but since you have it both in the business as usual and your scenarios, I mean, that's a minor point. But what happens with the revenue in your model? So even if it's allowances, you're auctioning them, so you have revenues. I was wondering, is it redistributed, or what are you assuming in your CGE model on the revenue?
The revenue that is coming from the CO2 price, right? You mean?
Yes.
It's basically revenue to the government that can use it for general. We didn't target a particular investment with this revenue. We just use it as general public expenditure. So,
and then okay. So it's not redistributed to households, for instance, because then that could give a demand effect. And
it's partly it's public expenditure plus redistribution to households. Yeah, it's basically it's having the same structure that it had in the base year in terms of redistribution, which means we are using economic speaking, we are using I believe it's a Cobb-Douglas function in this case for the household, for the government that is making purchasing services in general and commodities from the different sectors. So it's public expenditure, and partly we have transfers with a fixed coefficient depending on the savings, sort of, or whatever is not spent as public expenditure.
My other modeling question was about I don't think you model carbon intensity as such. Let me explain. You have that in the production of energy, but the demand side in industry, it seems to me you don't have technical change. You have only a scale effect and an energy efficiency effect. Is that true?
We are not modeling carbon intensity, but we are modeling energy intensity on one side, and we are modeling the change in sort of preferences. Let's say that if we had a Cobb-Douglas function, I were modeling the coefficients, what's called the power, you know. Yeah. So the exponents, yeah, that's so we are modeling the technical change, and but of the energy stack, of the energy nest, that's of the energy group of commodities, and we are modeling the energy efficiency by reduce. You know, it's a fixed, sort of a growing coefficient. It's a capitalization coefficient. Let's put it like this. That decreases the demand of the whole energy commodities group over time.
But fuel switching, then I'm getting to this issue. What about fuel switching?
Fuel switching happens for basically two reasons. One is the fact that Genesis Mod is proposing a new structure for the fuels. So for each sector, so each sector gets a new structure for the fuels.
Okay.
and they say, okay, now we are moving from, you know, let's say diesel to more electricity. And the second one, and partly for this, and the second one is carbon for the sectors that are not, you know, that do not take as input this new structure from the bottom-up model. For these sectors, we have the carbon price, and we have a very high elasticity of substitution between the energy commodities. This means that over time there will be a switch. They will move towards cleaner ones because the other ones are producing CO2 basically, and they will have to pay high prices for the allowances.
Eoin may have a question. Is that
yes,
so? Yeah.
Yes, thanks, Chair. Yeah, great work, Paolo. Just in the
Thanks.
In the basic scenario, the emissions fall quite a lot.
Yes.
And I'm just wondering if you can relate it to EU targets. Could you say how close to the targets it comes in the different scenarios?
Well, what we have used is I believe we have taken an initial trend that we had. I don't remember the source though. I believe that was given to me by my colleague from TU Berlin. But where we had an initial trend, and then we applied the same trend, and we ended up having this 60% decrease. But yeah, I believe that that probably even a lower amount would fit. I'm not sure if we have used this EU reference shetio, but
okay. You could include on your graphs a line which shows the EU targets just to see whether they're being met. Just with the two CGE models you were showing about, one is in quantities and one is in euros or money. Is it? I didn't really catch. Is it that you've made a hybrid of both models?
Yeah, it's not two CGE models. We have one CGE model,
okay,
and the other one is a energy system model.
Okay.
Which is basically, you know, what they get is the, let's say, transport-wise, how many kilometers per person is going to be driven by cars, and then how much usage of heating in the house is going to be, and so on and so forth. And they compute the energy needs for each of these by using a least cost. Optimal function, objective function. So at the end, they provide the energy needs using a very detailed system of the energy system of the European countries. The CG model, yeah, it has a very bad representation of the energy. It's not bad, but it's coarse. You know, it's very general. And by using information taken from a energy system model, then it becomes much more precise.
Okay, yeah. In CIRED, where I was for a couple of years full time, their model EMITLEAM is a CGE which incorporates the bottom up parts as well to get that rich representation.
Right.
So it's interesting to come across another group who are taking that approach.
Yeah, it's quite a trend recently, trying to link different types of models so that you can get the best out of, you know, not out of each one, but really as a sort of cohesive story of the different parts.
Let me just check if Gael is here, the third speaker, if he's arrived. Because then we can take more time for the discussions. Excuse me for interrupting. Otherwise, I have to pass on the word to our third speaker. No, I don't think. Gael, are you here?
Yeah, I'm here.
Yeah, it's you. Okay, great. So I'm sorry, Paolo, is that okay? Should we take one last question maybe, or if anyone has something from the floor? And then we pass on to the third paper. And I'm sorry about the delay. Okay, so thank you, Paolo, for your clear presentation.
Thanks.
Can you share your screen then, Thomas Gael?
Yes.
So our third paper is also on carbon pricing, rather the elasticities from the carbon allowance prices in the EU ETS, if I got it right.
Please, a moment.
Of course. And I apologize for the delay getting the session a bit late, but I guess we have a break, right? So it's not a problem if we run over by 5 minutes, hopefully for every one of you. We can see your screen now. That's great. Thanks.
It's okay?
Yeah, you just need to open it. So we see your... Now I see your abstract.
Okay, thank you. Hello, everyone. I'm Thomas Gael, Bebga Nguidjoi, a statistician, engineer, and energy economist by training. Actually, a PhD researcher in economics at the University of Chiang in Kampong. I will present you an extended abstract on interaction between carbon price and electricity price in Europe in the case of France and Germany. For the overview, since 2005, as part of Kyoto Protocol, the European Union has implemented a trade plan to limit carbon emissions, and each year allowances are allocated for industrial carbon emitters. This climate policy also result in the cap and trade program for carbon, and will result in increased business spending. According to the International Energy Agency, the statistics is showing that the energy sector contributes to 40% of carbon emission and has that have a significant impact on the energy industry. We shall never, in a study on the impact of carbon allowance price in retail electricity price, distinguish the factor likely to have an impact on electricity price. And as electricity is vital for economic input, the impact of fluctuation in electricity price could have also an impact on the entire economy. The main objective of the work was to describe the interaction between carbon price and electricity price by an econometric computing. The method we use an econometric modeling to quantify interaction between carbon price and electricity price. And the description of the method is that firstly, we have to determine the degree of integration of log variables using a Dickey-Fuller augmented uni-root test. After this, we test co-integration of log variable using the Engel and Nguidjoi test or Johnson test according to the integration order of the variable. Then we estimate, after the co-integration test, we estimate the error-corrected model by the ordinary least square method. And the interpretation of the coefficient of the model is given, is interpreted as short-term and long-term elasticities. We use data from IPEC spot, and our series started in 2010, and it is a weekly data. And it concerns only electricity price and carbon price in France and Germany. We will present the sample results that we obtained for the test. For the degree of integration of log variable, we choose CR, which is a certified emission reduction. For this series, we work on a log variable, and this table shows the result that indicate that with constancy, this series is non-stationary, because the aim to use an error-corrected model, we have to have a stationary variable, and we have to compute the test with constancy and tendance, and with no constancy and tendance, because we have to work with stationary variables. After computing those tests of integration with log variable, we carry out a stationary test and we use a Johansen co-integration test because of the level of integration of our log variables. And for all that test, the co-integration hypothesis is accepted if the value of the statistic is greater than the critical value. Our critical variable here is 5%. And for the error correction model approach, the estimated was done by ordinary least square error corrected model, well done by Henry one-step estimation. And the equation, our model equation is written like you can read on the screen. The first two equation is for France, and the two last equation is for Germany. If we choose the first equation, we have the dependent variable log of price of electricity in France, and the independent variable, we have a log of CER carbon, and we have a log of electricity price retarded, and log of CER retarded. And the result of the model estimate for France, for Germany, that's for Germany, because we have more tables, we can't in our extend abstract put all there. We note that the coefficient associated with the force of return equilibrium is negative, minus 0.39, and significantly different from 0 at 5% 3 hertz. There is therefore a correction mechanism in the long term in the imbalance between European Union price and electricity price in Germany are offset, so that the two variables have similar development. At the end of this calculation, we can also present some sample of graphics. That's, for example, for France between 2010 and 2012. On the screen, we can we see that electricity price have the same evolution with the carbon price. When electricity price rise, carbon price rise. When it decrease, carbon price decrease also. Here we have the evolution of carbon price and electricity price in France and Germany, and we see that for electricity price is very between 2010 and 2012. Electricity price in Germany is running the level is too high than in France, and carbon price have also the evolution according to electricity price in those countries. Globally, the following results obtained show that the long-term elasticity is 0.3 for CO2 CER in France and increased by 10% than electricity price in France for the short-term elasticity. The long-term elasticity for long-term elasticity is increased by 0.05%. That's for CER emission. And if we take the case of Germany for the European Union allowance, we see that the short-term elasticity increased by 3.2% for the short term in Germany, and the long-term elasticity increased by 1.5 in Germany for European Union allowance carbon. In conclusion, overall, the work we done with the aim to quantify the interaction between carbon price and electricity price in Europe, depending of the availability of the information collected in France and Germany, it emerged that in the short and long term, carbon price has an impact on electricity prices in France and Germany. When carbon price rise, electricity price increase also. We have some references that help us to produce this abstract. PowerNet, EPEXPORT, CIRE, Cher Économie et du Climat, and the International Energy Agency. Thank you for your kind attention.
So let's have a discussion. There are questions or comments? Yes, please.
Katie, Thomas, what's the difference between the two CO2 variables? You've CO2 EU. Can you tell us that?
Yes. CO2 CO2 European Union allowance and CIRE these what are used on the European Union emission trading system. CER is for certified emission reduction, and it is a type of emission units. And the European Union allowance is the official name of European emission allowance. Is the difference between the two concepts, carbon CER and carbon EUA.
You're trying to link the emission reductions from the CDM with the EU ETS market?
Is it a question?
Yes, because
Could
CER
you-
is from the CDM, right?
Yeah.
To follow up on Eoin's question. I don't understand why you finish. Which year do you finish in? Your data, epics that you use.
That we wish to have new data to improve our model. We asked from IFP when I done my training program, and for expert, but we don't get new data to.
No, sorry, what's your end year? You start in 2010, and what's the end year of your epics data?
For what I present,
Yes.
we present weekly data from 2010 and 2012.
Okay, because yeah, sorry.
Yeah.
No, I don't understand that because, you know, do you know the paper by Ibrahim Ahmada and Jamel Kirat, 2015? So I think I believe they use the same data as you do, the epics data. And they look at phase 2, it seems to me, of the EU ETS. So that will be 2008 to 2010. And I believe there are other papers. So I would think you could turn to studying more phase 3. So look at the later data since that's available now, if you can get it. I mean, I'm not doing research on this. I can imagine it's difficult. So, I mean, I would encourage you maybe to go and look at phase 3, 2013 onwards, right? Or the EU ETS to do a contribution to this analysis.
Okay, I will do it.
And I also believe that Jamel Kirat has a paper with Claire Gabard on this issue of comparing the impact of coupling the external mechanisms with the EU ETS. So comparing the influence of CER and EUA, which I believe is what you want to do, right?
Yes.
Yeah. So that could be nice to discuss with them.
Okay.
Do you have any idea of why there are differences in the elasticity, in the impacts in France and Germany?
Yeah, good question. I was going to come to that too, because you have a higher elasticity in France than in Germany, right?
Yeah, we have a higher elasticity, short term or long term. For short term, if we take the case of France, for short term, in France for CR, we have a high elasticity in France than Germany, and for long term we have a lower elasticity for CR, and if we take the case of EUA, in France we have a high elasticity, and in Germany for long term we have I think the comparison was be done for specify elasticity. In France,
It must have something to do with the energy mix, right, of the two countries.
Is there any comparison that I made for the energy mix?
What is the reason for the different results for the two countries?
The reason the reason is there for the two countries, the energy mix is different because in France we have in France they use more nuclear than Germany, and Germany is now decarbonizing her energy system. They move from clean energy, and I think if I get the recent data, the recent data will more explain why we have those difference. It's for the energy mix. In France, we use 70% of nuclear, and in Germany it is lower, and they promote now the use of clean energy like renewables.
But shouldn't the elasticity then be lower in France if you base it on that argument? This is what's surprising with the difference in the estimates. Any other one wants to jump in for a question or comment? Also on the previous papers, if you felt you haven't had an occasion, I mean, Paolo is still here, Eoin is here.
Thomas, what software do you use to do your regressions?
Could you repeat the question, please?
Do you use like Stata or 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 what?
EViews, we compute with EViews.
Okay. Yeah.
EViews
Okay.
software.
There might be functions where you can try the ARDL bounds approach, and then it doesn't matter if the time series are it doesn't matter what order, if they're integrated, you know, if they're I0 or I1, if you need, it doesn't matter whether you need to difference them to make sure that they're stationary.
To make the stationary test, to make the co-integration test, we must use variable that are stationary at the same level. Yeah. They can be integrated in level 0 or in the first difference.
Mm. Mm. There's another way to do it where you don't have to do those tests. It's called the ARDL bounds approach.
Okay, good suggestion.
I'll just put it in the chat.
Mm. No, thanks.
What I learned for the moment is DAE approach. I don't know if there is a new approach for to determine the degree of integration of variables.
Yeah, so Eoin put it in the conversation box, if you can see it now.
Okay.
Okay, so unless anyone else has a question, I guess we should finish on time, and I should thank the three speakers, Thomas, Gael, Eoin, and Paolo.
Thanks.
And enjoy the rest of the conference.
Thanks, Katie.
You too. Bye.
Great to meet you.
Thank you. Bye-bye.
Okay. Thank
Bye,
you.
everybody.
Have a nice day. Thank you.